Hi everyone, thanks for joining me virtually today. I'm here to talk about high performance computing in the cloud. So let's get started. My name is Greg Cormier. I work for Fisheries and Oceans. I started my career as a web developer, and since then moved through managing corporate applications and systems, and more recently sort of playing a role in shaping and guiding where DFO heads in the cloud. On this journey. So I'm not a scientist at all. I'm an IT, I'm a techie, and I'm also not an HPC expert. So if you are an HPC expert, this talk could be, a bit painful for you, a little bit cringy, but try and bear with me. Target audience, we're going to start with some broad high-level, ideas about HPC, but then we're going to dive down pretty deep into the actual tech and some of the work or experiments I've been doing. So really, I think my goal here is to brain dump in, 25 minutes if I can, sort of everything I've learned along the way. So really just, trying to compact that knowledge, share that with other folks who are maybe just techies and not HPC experts into, if there's something you can do to help your department in HPC, how can you get started and how can you, go through the same steps I went through. So some brief terminology. HPC, high performance computing, is what we're talking about. CSP, cloud service provider, is Amazon or Azure. InfiniBand or IB, that's just a really fast network. We'll talk a little bit about it. CPU bound is something in which the CPU is a limiting factor. So we'll often talk about CPU bound, memory bound, network bound. So the limiting factor in your workload. And finally, MPI, message passing interface, which is a communication protocol, really specialized to handle parallelization of tasks in a computer. So we'll start with what HPC is not, because I sort of ran into this. In talking to some people at DFO, I started building a network of scientists and talking to them and what their needs were in the cloud. And, I mentioned HPC and that we would be interested in doing HPC with some folks at the department, if only I could find them, right? And so they said, oh yeah, absolutely. I know someone you can talk to about it. So I said, great. Get on the phone with this person and talk to them. Great, you're doing HPC, what do you need? And they say, yeah, I need, my desktop's too slow and I need to get a VM in the cloud with 16 cores. So I sort of thought, well, that's not really HPC. That's just, I won't even say it's a lot of cores. It's just 16 cores. So we can definitely provision that for you because we do offer our scientists the ability to run virtual machines in the cloud, but it's not really HPC. It's not what I'm looking for. So just be aware of that in your search if you're looking for analyses. And of course, I'm making a generalization, and as we'll learn, those don't go well in HPC. So we'll talk a little bit more about this later. So what is HPC? A nice Wikipedia definition, but the application of supercomputers to computational problems that are either too large for standard computers or take too long. So if you want to, forecast the weather on your home PC, it might take a week to figure out what the weather is going to be tomorrow. Obviously, that's not really useful for anyone. Or maybe it's just not even possible at all. Maybe you don't have the memory and it wouldn't process, it would crash, or you wouldn't get any output. In talking about that, it's not just about the computers, but the networks that connect them together, and then how you store all that data, right? So, what you'll quickly find out, one of these will be your bottleneck. So with HPC, you may be jumping between them. So as soon as you've solved one bottleneck, you'll just be sort of limited by another one, or more likely you're going to come up against a bottleneck such that you can't solve it. So you've thrown, the fastest networks in the world at it, or you've done the biggest amount of cores or whatever it is, and then you're kind of going to be stuck at that point. And then finally, we have a software layer in there for the work itself and also scheduling these. So if you've built up a large HPC cluster, a supercomputer, you're going to be scheduling these tasks. You want a queue, you want these resources to be busy calculating things all the time. So that's really important. So part of this, the idea of HPC is building it, but then also having the tools in place such that, one or many scientists can have jobs running 24/7. What else is HPC? It's Fortran. I never thought I would be installing a Fortran compiler, let alone compiling Fortran code. Um, I just can't believe how much HPC sort of ties back to Fortran, at least at the examples I've looked at. And so, Fortran wasn't, or sorry, I wasn't around when Fortran was a thing, but it still seems to be there. So if you do have that sort of skill in your back pocket, it will be very useful. I think there is a general shift in looking towards new technologies to take over from Fortran, but a lot of work has been put into some of these models, I imagine, that scientists are using. So I think there's still Fortran will be around for a while to come. So to set the stage a bit, HPC and cloud, doing HPC and cloud, it's not the easy button. You don't just sort of do it and everything's going to be solved and you're done. It's another option. So we've, just like any other workload, if you have, a web application or any corporate system, cloud gives you options in how you could solve a potential problem. So, can you understand your current workload? Choose some pain points that you have and see if cloud can help you solve maybe some of those, maybe all of those if you're lucky, right? So, don't make assumptions and say, going to cloud is going to fix everything. And as always, not everything is black and white, right? So there might be some give and take in moving to cloud and bringing these workloads over, but it's going to be up to you to really understand what you're doing today and what you'd like to do better, and if moving to the cloud is going to help you do that. So with that said, HPC data centers are a massive investment. So lots of cores, really fast networks, lots of really fast storage, right? So typical capital expenditure, you need to buy these, this hardware, build a data center and run these things. So what's nice with cloud is you can sort of let the cloud service providers worry about that life cycle. So if you're coming up, on a refresh, you need to go and buy a bunch of new hardware. Instead, these cloud service providers, they have these hyperscale data centers. So what we're provisioning today to run HPC calculations, in 18 months, that might sort of be downgraded to the fast server type in Azure AWS. And then maybe 3 years from now, that our HPC server today is going to be that developer who's looking for the cheapest possible server he can find in the cloud. He's going to maybe end up running on that hardware. But it's a black box. You don't have to worry about that. And however the cloud service provider wants to deal with that, that's great. That's on them. You can just take advantage of the fact that they're going to have cutting edge hardware ready for you. Once you're in the cloud, if you're doing your HPC workloads in the cloud, you can take advantage of everything else that surrounds, your typical cloud service provider. So you might have some data lakes. You could be doing your, offline analysis on a really big VM in the cloud, right? So if you have that output data set and now you need to download it on your laptop and you're running on 4 cores, or you have a corporate image, which is maybe a little restrictive, do that in the cloud instead. That's where your data is going to be output, so you might as well keep working there. Maybe archiving data, so if you have intermediate data sets which have some value for a period of time, or you do need to keep them, you could just archive that directly from the cloud. And also spot instances, so taking advantage of cheaper, I like to call it the eBay of cores, but take advantage of cheaper core hours on demand with the cloud service provider. So you'll have to do that cost-benefit analysis on how cloud best suits you, right? So can you run maybe one-off workloads on the cloud? So if you've got a scientist that maybe has a very, specified period of time they need to run a workload, or they've got a project where it's like, I need to run this analysis, then I'll get my results, I'll publish, and I'll be done. Or maybe you've got some smaller workloads, which would almost be like noise if you do have an HPC provider that's running a lot of your workloads for you. Maybe it would just be like, well, rather than going through all the work of getting that into our main HPC platform, we'll just do this one off in the cloud and you'll be done. Or likewise, can you save your on-prem cores, right, for dedicated or maybe classified workloads? So right now, you can run unclassified workloads in the cloud, HPC workloads. If you move up to the protected level, will your cloud service provider, will there be enough demand for them to bring these really specialized instance types to Canada so that you can run protected A or protected B workloads. Not sure. So, run what you can in the cloud, and then you have more on-prem cores maybe for the weather forecasting, which is going to be ongoing, or like classified workloads that I think is safe to say they won't be on the cloud anytime soon. And finally, really, I think the flexibility is key, right? So, cloud is flexible, it's agile, we can break down that barrier. So you can get access to cores right away. You can try something out. And, some of these HPC providers, you need university affiliation to gain access to it. So that can be a barrier to entry. You can also define and evolve your hardware needs as you build or mature your workload, right? So if if you have some uncertainties surrounding what you're trying to run, you can play around in the cloud. So let's say you think you need a lot of GPUs to run your workload. So you go out and you buy a bunch of GPUs and you build up that data center, or you go to your HPC provider and you sign on and you say, yeah, I want GPUs, it's going to be great. And they get it for you, say, here you go, that's great. Then you run your workload and you realize like, that didn't actually run as good as I thought. Or like it still runs, but I guess for cost benefit, maybe I would have just ran it on a CPU. These are all just hypotheticals, but with cloud, you can actually go and spin that up, and you can try it on a GPU or 1,000 GPUs. You can try it on CPUs and see if that's going to work, right? Again, making naive assumptions that your code will run on a CPU versus a GPU, which is likely not the case, but you can make those informed decisions. And then either, you go cloud because it works for you, or maybe then you say, okay, GPU is the way to go. So you sign on with your HPC provider and you say, yeah, like I do need, 1,000 GPU cards to run my analyses. And finally, sticking with cloud, you can shop around between your CSPs. So it's a very competitive market, and the big three, right? We've got Google, we've got Amazon, we've got Azure. They're leapfrogging each other in tech all the time, and they're looking at what each other's doing, and they want to up each other. So as a consumer, it's great to be able to take advantage of that. We've done that at DFO, right? We looked at Amazon and we looked at Azure, and we looked at some of their, we did a comparison between InfiniBand and the Elastic Fabric adapters on Amazon Web Services. So really fast networks, whose is faster? And so at the time it was Azure. Will that change? Very likely, but it's pretty nice to be able to do that rather than just buying it and having that technology in for your 3 to 5 year period perhaps. So delving into a bit of sort of the specifics of things I've learned. You got your CPUs or your cores, just fastest cores and you're done, right? Well, there's some sort of nuances that I found was hard to communicate to scientists because again, they're not always in the nitty-gritty details of the technical details of a server. So you'll have a speed of a core in gigahertz. Sometimes there's differences in the same speed of cores, be it between Intel and AMD or even within the same processor, right? So a processor could have more cache. It could have bigger memory bandwidth. So how quickly can that processor talk to the memory on the server? And then all-core turbo, which is underlined, really important. That just says, in a multi-core processor, how many of these cores can actually run at full speed. For some of them, if you take a 16-core processor, you might actually only be able to run 4 cores at full speed, and then things start to slow down if you try and hammer them harder than that. And of course, with HPC, we run almost all the cores at 100% all the time. So really, an Intel i7 in a laptop versus desktop versus server, it comes down to money and heat, right? An i7 in your laptop, you buy the top of the line Dell or Surface, that's not the same CPU as an i7 in a server, right? The amount of heat that these things need to get rid of, you just can't do it in a laptop. It would just be a giant fan you would be carrying around. So making sure you understand those differences is really key to, I think, look at the workloads, talk to the scientists and see what their expectations are, right? Make sure you're looking at physical cores. So a couple years ago, cloud service providers, I can't remember who started it. It was Amazon or Azure, but one of them was advertising cores. The other was advertising threads. So if you have a core, we often have Intel hyperthreading, which means one core can run 2 threads at once. And sort of it handles some of that that context switching. Now I think all of the cloud service providers are on the same page, and just read the fine print. They'll talk a lot about vCPUs. Typically speaking, they're referring to threads. So you need to cut that number in half. That said, the HPC instance types on Azure, they do refer to physical cores. So, moral of the story, look it up and find out. If you provision your VM, you can, log into Linux, look at the actual make and model of the CPU you've got, Google it, see what it is. So if you're dealing with Intel, it's going to be on the Intel ARK. You can find out all the details about their processors. You can find out the all-core turbo speeds, and you can, figure out that, okay, an Intel Xeon Platinum 8168 is actually 44 cores, and that's how it is advertised on Azure. So make sure you're looking at cores, because that's going to be important, because you might find that it's running half as quickly as you'd think, and it's because it's actually, you don't have the cores you thought you had, you just have those threads working. Memory and disks. So for HPC instance types, generally you're not going to have much selection, right? They're going to say these are the types to choose from. They're going to have a preset sort of ratio of core to memory. If you don't need, in the case of Azure, if you don't need InfiniBand, you can open up your instance series selection to other types, right? So you could pick one that maybe has a few less cores and a lot more memory. Some of these M series have 2 terabytes of RAM on them, right? And relatively few cores. But if you have a calculation that really needs a lot of memory, maybe that's the one for you. As for disks, generally speaking, the bigger the instance, the bigger and faster the ephemeral storage, right? Ephemeral storage, just fancy word for temporary. So you'll often see in Azure temporary disk allocated to your instance. So when you turn it off, that disk is destroyed. Make sure you use it. It's free, so don't provision extra storage if you don't need to. If you need more I/O, this is where you're going to have to look into HPC-specific network file systems. And I'm calling this the danger zone. I didn't run into this. The workloads that I was looking at were very CPU bound, right? The CPU was just melting, and the network and the storage was basically snoozing while they were calculating numbers. I think right now a cost-effective, supported high-performance computing file system in the cloud is a challenge, right? If you're looking at something like Lustre or other products, this is really like an enterprise offering. So you need to have that HPC provider that says, we do HPC, and yes, if you need Lustre, or you need like blazing fast I/O that all of your worker bees can sort of talk to at the same time, that's going to be a big undertaking to do. So if you're just dabbling around, it could be challenging if you don't have someone who's ready to commit to this for you to build it out. And finally, storage. You're in the cloud, right? So make sure you take advantage of blob storage, because you don't have that on premise. So it's kind of nice if you have that workload, maybe either as the workload's going, if you can just start putting those files up into blob storage and freeing up that local solid state drive to keep taking on more output, great. Or when you're done your job, just dump it all in your blob storage, and then you shut down your node. So make sure you use it. It's really cheap, and I think that's one of the real big pros to doing your HPC in the cloud. And last and certainly not least is networking. And that's the key component that can affect your workload. So we talked a bit about InfiniBand just in the acronym section. So I quickly learned, or dove into the world of InfiniBand. And it isn't about the bandwidth, and especially with cloud, where bandwidth is just getting so ridiculously big. It's really about low latency and some other stuff too. But if you have 1,000 worker bees across multiple servers, they're all talking to each other. That time between messages becomes really important. So imagine if we're in a room and we're playing the game telephone, where we each pass a word to each other, right? And if it takes 1 second for each of us to whisper that word to the next, there's 1,000 people. It's going to take us, at least 1,000 seconds to get that message through. So the same thing applies to, your workload. Some of these, these computers are processing really fast. A tiny delay in the network to get that, message, to pass things in between them, can slow them down a lot. So it's really about reducing the latency between, all of your nodes that are talking to each other. If you don't need really low latency, and I think that, a great example of this would be like a render farm. So if we take Pixar and they're rendering, Toy Story 3, they've got this movie and they've done it all, and basically a render farm will just take all of these frames to build up the movie and send it out to all these, a farm of servers. And none of them care about what the other ones are doing. Their goal is to render a frame, and that's it, and send it back and they're done, and do that over and over. So, something like that, you can just use any cloud instance type and a lot of them together. And if we take like a standard F72 on Azure, you're going to have, 36 cores because, again, hyper-threading, right? So 36 physical cores, you're getting 30 gigabits of bandwidth. It's not going to be that low latency InfiniBand, but, that's plenty of bandwidth to move data around. There's a link here that talks. It's an Amazon reInvent video. It's about an hour long, but it's really good. It talks about sort of HPC and optimizing network performance on Amazon, right? So they cover things like overhead into, things like TCP, overhead in drivers, in interfacing with the hardware and how they bypass it. And I think it's a really interesting talk to watch. Even though it's Amazon, it's sort of the material applies to anyone, no matter what you're trying to do in reducing network latency. So HPC on Azure, as I said, we've run this workload on both Amazon and Azure, but we did get better results on Azure using InfiniBand. So I thought it was interesting to look at the timeline, and again, talking about sort of the speed at which these cloud service providers are moving. So you can see here the generations as they move through, right? And even if you look at their backend networks, so these are InfiniBand networks for their HPC instance types, it's just screaming, right? You're going from 56 gigs up to 200 gigs. And then this last box here, I've got Microsoft Ignite 2020. So I'm actually recording this before Microsoft Ignite is taking place, but I think I'd be silly to not look at fall 2018 and fall 2019 having major announcements on the HPC instance types. Hopefully we'll see something, be it at Ignite or sometime later this fall, an announcement from Microsoft on, again, the next gen HPC instance type, right? And this is just, you just get it when it becomes available just by using the cloud. And so if you're already in there running your workloads on there, instead of, your workload provisioning 10 HP 120s, it's going to provision 10 of, maybe the new instance type that comes out. So starting from scratch for the actual HPC workload, it's called FVCOM, and there's a nice definition here. I won't even read out because I'll just butcher it, but it's all sciencey stuff, I'm sure. But really, for me, the goal is to get this running in the cloud. And as I mentioned, CPU bound, so it wants really fast cores thrown at it all the time, and it's very happy. So I looked at sort of the world of HPC, knowing nothing at all whatsoever, and you get down the rabbit hole of schedulers and all this, but really I just wanted to get it running to see, is this an option for DFO? Is this an option for our scientists? And are they even interested in paying for this? So if you build it, they will come. I've been burned by that before. I didn't want to invest the effort. So really I'm aiming for a minimum viable product to get benchmark numbers and really prices to hit the scientists with, say, this is what it's going to cost you to run your workload. So with that, I just took my IT, background and applied it to this problem, right? So to start with, it's building that base image. So I use Packer, which is an open source tool, which, strives at building your golden image, so to speak, of your operating system and packaging it all up in the cloud. I can work on premise as well with VMware and whatnot, but it does great in the cloud. So with this, I install all the typical packages and the dependencies that are required. A lot of compiling happens, configuring InfiniBand in the case of an Azure instance. And this doesn't happen very often, right? Packer is like a build your image, it's ready to go. So you have that golden image, and you can spin it up whenever you want, right? And this is where I think, another benefit of cloud is that there's an opportunity here for scientists to define their own standard gold image with specific versions of libraries they need. So if you have one group of folks that are doing ocean modeling, maybe they want a very specific set of software, right? Certain versions of HDF or MPI, and they'd like to stick to that because they want to keep it consistent. You can build up that image in the cloud and have it ready. Whereas another group might have a completely different set of libraries that maybe there's some conflicts or some issues between them, but this is what the folks in their community are using. So, profit from that. Using the cloud, just cook up a ton of different images, and then they can also define, the ones they want. They could even go and when they publish their findings, they could even say this is the exact version of everything we used. And by the way, here's a link to our Packer image. If you want to go and try and reproduce our results, you can do that. So pretty cool stuff. So finally, once we have that image, it's ready to get stamped out. The next steps is actually doing your science. So I use Terraform to provision the instances. So that's going to spin up anywhere from 1 to n VM. So it could be 1 VM, could be 10, could be 1,000. Of course, today Azure is limited to 200 virtual machines in an availability set, which is you need to put them in an availability set for InfiniBand so that they're all sitting close to each other in a single data center. But that's it. Terraform will create, let's say 10 VMs, and then they're sitting there idle, ready to go. So at that point, I use Ansible, which is a great, again, these are all open source tools, configuration management tool. So with Ansible, I say I got 10 nodes. They've got my, my image that I built ready to go, but what are they supposed to do? So Ansible has them each download a data set and the working files they need from blob storage on every node. So again, take advantage of the cloud, right? I've got 10 nodes running. I've got my data sets in blob storage. To download, tens of gigabytes, hundreds of gigabytes can happen really quickly on your VM in the cloud, especially with these really fast instance types. Generally, the network performance of your VM scales with the size. So a tiny little dev one core VM, it's going to max out at, I don't know, let's say 100 megs. Whereas as we saw a couple slides before, these big ones get many gigabits of bandwidth. So download that data set, and then on the master node, we just start the workload. And then it handles all the communications between all the nodes using MPI in this case. And then it is able to output all of its, the work after it's done to the drive. And then we upload the results to, again, blob storage and the logs as well. And then everything is destroyed, right? We terminate all the instances. It's a Vdoo cloud, so we stop paying for it and we're done. So at the end of it, I've got a storage account. Early days, it was always filled with logs with errors and no actual data. But now, it's filled with data. And of course, this just works for FVCOM, what we were looking at. The input data set was relatively small. The output data set was a little bit big, but if you have a huge input data set, you're hitting that danger zone of needing somewhere to get it from, maybe getting into that high performance file system. Maybe not, maybe a network file share would work for you. That's, it's sort of, again, up for you to investigate. Down below is a GitHub link to basically not the scripts, but all of the stuff for Packer, Terraform, and Ansible for AWS and for Azure, the tools I use to sort of build out these images. And then you'll find the do science shell script, which sort of invokes each step and gives the output. So the results. This is what we found. So these were over a period of maybe 8 months because some of these new instance types were announced, so I want to try them out. But we've got total runtimes, number of cores per instance, total cores, total cost. So it's interesting here to see sort of all the permutations, and it's overwhelming, right? And in this case, this is a 1 month model we're doing, and it seemed to make sense to try a 1 month model to benchmark and try these various permutations. But you could spend weeks just fiddling knobs and trying to squeeze out every last iota of metric from these CPUs. But I think what's interesting, so if we just look at the last three. And these are the latest and greatest instance types from Azure, right? We've got 1 instance, 2, and 3. So at 2 instances, you can see 190 minutes, 240 cores, $25. And then if we go to 3 instances, you can see where it starts to kind of slow, it's not scaling well, right? The runtime is low, but we're paying a bit more because the overhead starts to to kick in, and that's going to happen with every model from what I'm told. Like, it just depends on the model. Some of them scale really well and you get into thousands of cores. Other ones, and working with some of the genomics guys, they sort of fall on their face after 8 cores or 16 cores. Like, they can barely be parallelized. Some of them run on 1 core still because it's a sequential calculation. It can't really be split up. But what's kind of cool is if you look at the single instance count in the middle, the HP120, it took 370 minutes, so about 6 hours, which would cost $24, but we can actually do spot pricing. And so we can say, hey, like, I'll give you $8 for those unused cores while they're idle. So you can save a lot of money, which is kind of nice. And then we're also, at this point, at the start we said what HPC is not. It's not, a nice big computer. Well, maybe it is, right? So with this one, you're just dealing with a single virtual machine. So that scientists, they don't need to look at network file systems. They don't need to look at MPI, InfiniBand. They're just logged into their Linux VM and they just run their calculation. They go away, and then when they come back, it's done. And it's like, the world, it's analogous to like that, computer under their desk that a lot of these scientists have, right? That's sort of stashed away, and it's, they managed to get their hands on one. It's just a single server, and so it's something they could work with. But buying a 120 core server to stick on your desk is not a great idea. So you have an on-demand access here to a really fast server. But in any case, we do have them working as a cluster, and it seemed to work out quite well. And it was what the scientists expected to see. They didn't expect it to scale up to hundreds and hundreds and hundreds of cores and see like a linear return on that. So overall, I think good results and very promising. And, it's nice to see these massive instance types available just to someone like me who doesn't have any affiliation. I'm not a scientist. I can just go in and spin these up and try them out. So the next steps for us, or for me, is to keep looking for proof of concepts in the department to find candidates, right? I need to find someone interested enough to invest in the switch to HPC on the cloud, right? They have an HPC provider now, or they have multiple ones from my understanding. So, right now they're thinking, well, things are managed for me and maybe I've already paid, the price tag on my HPC cores, so I don't need to do it yet. But, we need to keep working at this and figuring it out, because we don't want to be waiting to the last minute to say like, hey, I'm sort of out of core hours now. I need to renew. Can you do this in the cloud? Well, unless we sort of do this exploratory work, we don't really know if we can do this in the cloud, right? Like I said at the start, it's up to us to kind of look at, does it make sense to do this? And then, build out that platform for scientists, right? Get a team in place to fill in the gaps, because really the scientists, they don't care so much about the nitty gritty in HPC, right? They just want to, do science. They don't want to learn about InfiniBand. They barely want to even like worry about compiling things in Fortran or library dependencies. They'd really like their, their workload to run, and they get their outputs and they can go, start looking at the results. That's really what interests them. So having a team in that middle layer is important, because, you certainly don't want to throw them at Azure and say, well, here's your account in Azure and they have InfiniBand, so I guess you can do HPC now. That's not going to work out very well at all. Something else I want to touch on, which is not quite HPC, but it really is along the same vein, is a project we've been doing recently on genome sequencing with some scientists at DFO. So, I think this is another good success story for us, in that, sequencing can't run on DFO's hardware. It just, you don't have the power, it doesn't have enough memory, you can't buy these things. And running on affiliate clusters, so the queue times can be really painful. So, that's undesirable. And then we also have like a hard cap of 20 terabytes on these, on the instances they're given. And, I'm told that the 1000 Genome project that they're looking at would need 120 to 150 terabytes of intermediate files. So it's not even like a nice to have, it's almost a necessity to go cloud, because it's like, with what we have access to today and what we're using today, we can't do it. And so there's, this opportunity to try cloud both from like a raw infrastructure point of view, so cores and disk space, but also workflow improvement, right? So we can modernize the tool sets used, and maybe get some, there's a potential to standardize what's being used by the scientists here. And that's, I owe that to the actual scientists that I'm working with, right? That's on them if they want to improve their actual workflow, right? But this gets back to that barrier to entry, right? We can, we don't need affiliation to get here. We can just try this and see if it's going to work. So what we found was Cromwell and Azure. So Cromwell is a scientific workflow engine designed for simplicity and scalability. So, Cromwell and Azure is just, I guess, Microsoft's adaptation of Cromwell to take advantage of, Microsoft Azure. So there's a diagram here which shows sort of how it works. But I think what's nice is that, you're not locking yourself in. You are spending cycles on building out your, workflow for genome sequencing in an open tool that's managed by the Broad Institute in this case. So, let's say Microsoft goes out of business tomorrow, which I think is unlikely, but if that were to happen, you're not up a creek without a paddle, right? You're using a standard tool set and that the scientific community uses, right? But I think what's nice here is that we have access to the experts at Azure who can help us sort of transition from all of these shell scripts which run through the GATK sort of pipeline and do all these steps to one that, they've packaged up and it's been pretty nice, and they can help us, make this work with fish, sorry. And, again, showing my non-science roots here, a lot of this stuff is just Greek to me. So behind the scenes, it's basically spooling up Azure Batch and invoking, all of your jobs on very cheap, low priority nodes, and then outputting the results when they're done. And what's nice, I think, is that ultimately the scientist's interface to this process is a storage account. So they're not connecting to a server. They don't have to do any command line. There's none of that. They're basically copying a trigger file into the storage account. You go for a coffee, beer, vacation, depending how long it's going to take. And then you come back and you look in your output folder of the storage account. And in there is hopefully all your outputs. If not, a lot of logs with a lot of errors. But really, Cromwell and Azure, it takes care of the heavy lifting to sort of, do everything you need it to do. Now, you still need to write the workflow definition language files, the WDL files. That's on you to come up with all these steps. So, again, it's not an easy button. It's not like you just dump files there and it figures it all out for you. But if you do have that workflow running, and maybe you just run that workflow locally on your own desktop, Linux desktop, or maybe you run it on a VM in the cloud. But basically, when you're ready, you should be able to transition that to Cromwell and Azure and then just take advantage of all of these spot or low priority instances and very cheap. And Microsoft's, sort of human genome proof of concept was called the $5 genome. We don't have the metrics yet. We've been working with them to benchmark it, but I think we are looking around $11 for a genome of certain types of fish. So the scientists overall seem very excited for this because it represents like a nice way to sort of, analyze these